In this work, we demonstrate a platform for automated manipulation of single cells as well as drug-infused polymeric microbeads. Magnetic microrobots are fabricated using standard photolithography and are composed of SU8 negative photoresist combined with magnetite nanoparticles. Microbeads are composed of polylactic coglycolic acid, a biocompatible polymer that degrades with time, allowing chemicals to diffuse into the surrounding media. The microrobots are actuated using a set of coils integrated with the microscope stage. Despite the relatively close proximity of the electromagnetic coils, it has been experimentally determined that the cores have little effect on one another in terms of magnetic field in the workspace, and that an assumption of linear superposition is reasonable. For tracking the robot, the microscope illumination method is switched to fluorescence mode. The magnetic transporter is fabricated using an autofluorescent material, and the beads are tagged with fluorophores. Fluorescence-based tracking is an effective method to filter out all objects in the image except for the bead and the robot, and in turn greatly reduces the complexity and computational cost of tracking algorithms. We track the centroid of the robot and separately track the bead with the circle detecting method that uses the Huff transform. A PID controller is applied to adjust the position and orientation of the microrobotic transporter. In this task, we deliver drug-loaded microbeads to a chosen destination on an individual neuron. This capability enables us to simulate individual cells at different positions. We may load individual beads with one or several chemicals, and we may stimulate cells at different locations. We start by using a thresholding algorithm to determine the location of the cell body. The phase contrast image is converted to a binarized map of obstacles. Noise is removed from the image by using a particle size filter, and the obstacles are further dilated to ensure that robots do not collide with cells. We identify the initial location of the robot, the location of the bead that we wish to transport, and the final position by the cell body. We next apply a simple graph search algorithm to determine an appropriate path for the robot. The robots are designed to cup and transport individual beads, so the path is designed to require that the bead be approached from a position opposite the destination cell. In future work, we will locally interrogate cells with drugs, configure arrays of cells, and probe protein interactions.